Imagine being able to carry an entire fortress in a space no larger than a teaspoon. How can a deep ocean fish release a few tiny drops of clear liquid that instantly explode into massive buckets of gelatinous slime, enough to make a hungry shark cough and flee in complete panic? It sounds like magic, but it is one of the most brilliant defense mechanisms in the natural world. Let us watch it happen and see exactly how this impossible physics trick works. Picture a clear glass tank full of ordinary seawater. A tiny, almost invisible droplet of biological matter is dropped in. With just a gentle stir, a soft, milky cloud billows out with shocking speed until the entire tank of water looks like thick soup. That is hagfish slime. It does not just grow, it practically detonates into existence, expanding by a factor of 10,000 times its original volume. Just a few milliliters of exudate from this fish can become liters upon liters of gel in mere moments. The stuff is almost entirely weightless, yet it grabs surrounding water like crazy, locking it into a physical matrix. If a large predator takes a bite, that cloud floods its mouth so fast that the attacker is forced to gape its jaws, cough violently, and back away just to breathe. We are going to break down exactly how an animal carries almost no physical slime inside its body, yet can flood the surrounding ocean on demand. But first, meet the maker of this marvel. This is the hagfish. While it might look a bit like an eel, it is absolutely not an eel. It is a jawless vertebrate, a remarkably strange survivor from a truly ancient lineage of life on Earth. The hagfish lives on dark, muddy seafloors, ranging from relatively shallow continental shelves down to deep ocean slopes more than 900 meters below the surface. The Pacific hagfish, for instance, thrives along the northeast Pacific coast. It is a slow, infinitely flexible, and exceptionally patient creature that spends most of its life resting quietly in the cold silt. Take a close look at its flanks. Along each side of its smooth, scaleless body runs a perfectly dotted line of tiny pores. Those are the openings to its slime glands. A single adult Pacific hagfish can possess around 100 pairs of these glands, meaning there are roughly 140 to 200 individual slime cannons lining its body. Each one of those tiny pores acts like a microscopic fire hose. When the hagfish is grabbed, bitten, or even just aggressively prodded, underlying muscles contract, and dozens of pores can pulse at the exact same time. You can see small beads of clear fluid pop out, then instantly vanish as the surrounding water stirs. Within seconds, the body looks entirely smooth again, but the water around it has transformed. So what exactly is inside each of those microscopic glands? Think of two primary ingredients packed incredibly tight into a tiny pouch. The first ingredient is a cluster of microscopic mucus packets, functioning like tiny water balloons packed with sticky sugars and proteins. The second ingredient is a tightly coiled bundle that holds a single, ultra-thin protein thread, wound up like a ball of yarn stuffed into a grain of rice. That single protein thread is an absolute biological marvel. Fully stretched out, it measures roughly 10 to 17 centimeters long, but it is only 1 to 3 micrometers thick. To put that in perspective, that is thinner than a human hair by a factor of 50 or more. Thousands of these intricately packed bundles can fit into a single droplet of the fluid. When this highly concentrated mixture hits the surrounding seawater, a dramatic chain reaction begins. The microscopic mucus packets immediately begin to swell as salt water rushes into them. Through osmotic pressure, they rapidly pop open, releasing highly hydrated, slippery blobs of mucin into the surrounding space. At the exact same time, the thousands of coiled thread bundles begin to rapidly unspool. Picture tugging the loose end of a very tightly wound ball of yarn, and the thread just keeps coming and coming, stretching out far beyond what seems physically possible for such a tiny starting package. Now imagine mixing those two elements together in the ocean. Long, silky threads weave violently through the newly formed fluffy mucin clouds. They do not create a heavy, dense jelly. Instead, they form a sprawling, watery mesh. Almost all of the resulting slime is actually seawater by volume. The solid hagfish material makes up just a few thousandths of a percent of the final trap. The secret switch that activates this entire weapon is hydrodynamics. It needs motion. In moving water, those thread bundles are pulled apart and unravel fast, allowing the gel to blossom completely in under a second. In still, calm water, the cloud stays surprisingly small and loose. But the moment you shake it, or a predator thrashes, it wakes up and explodes in size. The faster the water flows, the faster the chemical bloom occurs. Scientists and engineers who test this incredible material in laboratory tanks regularly measure expansion jumps in the range of 1,000 to 10,000 times the starting volume. It is quite literally a biological system where a mere teaspoon of fluid instantly becomes heavy buckets of solidifying gel. Imagine what that feels like to a deep-sea predator. The water that was just seconds ago easy to breathe suddenly turns into an impenetrable parachute clinging across its delicate gills. Laboratory videos capture this perfectly. A fish takes an aggressive bite, and a pale veil immediately spills into its mouth. The predator instantly releases its grip, opens its jaws wide, pumps its gills frantically, and shoots water forward to clear the suffocating mesh. It is crucial to understand that the attacking fish is not poisoned. There are no toxins at play here. It is simply choked by a near weightless physical tangle that grabs the water and will not let it pass. For any animal that breathes with gills, every single breath becomes an exhausting chore. Even for predators without gills, like marine mammals, it remains a foul, sticky mess that makes them immediately rethink their menu choices. While the predator is busy choking on the freshly made gel, the hagfish executes a beautifully neat escape move. It ties its own flexible body into an overhand knot. The tail loops around and then slides forward along its length like a squeegee. This knot physically scrapes the slime off its own skin, pushes hard against the confused attacker's face, and gives the hagfish a firm handle to pull itself completely free. That exact same knotty flexibility helps the hagfish at dinner time too. Hagfish are scavengers that often eat from the inside out, burying themselves deep into a carcass. They push into soft spots of dead fish or whales. Tying a knot gives them the mechanical leverage they need to brace against the surrounding flesh, to hit the brakes, or to peel away tough tissue. It is mechanically brilliant, and it works flawlessly. If you want to understand just how much slime this defense mechanism can produce at a massive scale, look at an event that occurred in Oregon on July 13, 2017. A transport truck hauling about 3,400 kilograms of live Pacific hagfish tipped over on Highway 101. The water containers burst open, tossing the stressed fish across the asphalt. And the fish simply did what they do best. They slimed absolutely everything in sight. The resulting mess was unbelievable. Cars, trucks, and the entire roadway were coated in a layer of clear gel several inches thick. Highway cleanup crews literally had to use snow shovels and heavy machinery to scrape the slime off the pavement. It was deeply gross for the drivers, but it was also a globally perfect demonstration of their expansion power. A handful of microscopic threads rapidly became hundreds of buckets of thick gel in a matter of seconds. This astonishing survival trick is by no means a recent evolutionary development. Hagfish are members of an incredibly ancient group. In 2017, scientists published a paper detailing a fossil called Tethymyxine from the late Cretaceous period, roughly 100 to 95 million years ago. Remarkably, this ancient fossil had preserved slime glands. That discovery firmly anchors this bizarre chemical defense deep in the history of the oceans. There are even older fossils that strongly resemble modern hagfish, dating back over 300 million years. though the specific details of their soft tissues are still fiercely debated by paleontologists. Regardless of the exact timeline, one thing is certain. The biological slime gun has been actively tested and perfected against the ocean's greatest predators for tens of millions of years. Life for a modern hagfish generally runs in the extremely slow lane. They thrive on quiet, muddy ocean bottoms, often in environments with very low oxygen levels that would suffocate other fish. Their resting metabolism is so impressively low that they can easily go for weeks and sometimes even months between meals. They do not sprint to chase down prey. They simply wait for the food to fall to them. When a large bounty of food, like a dead whale, finally sinks to the bottom, the hagfish arrive. They slide smoothly into the dark carcass and get straight to work. Soon, rival scavengers show up to steal a bite. But one accidental nip on a hagfish triggers a pale bloom of slime. The crowd of scavengers recoils, flushing their gills hard to clear the mess, while the hagfish happily keeps eating, completely unbothered. The slime does not just save lives, it guarantees a quiet lunch. So what about the remarkable threads themselves? They are not made of silk, and they are not made of collagen. They are composed of intermediate filament proteins, the exact same general class of molecules that provides many of our own cells with their internal scaffolding. Every single thread is ultra-fine yet incredibly tough, displaying an elasticity and strength that has materials scientists highly intrigued. Engineers are now asking if we could copy this biological system to manufacture strong, highly eco-friendly fibers, or perhaps hydrogels that can form incredibly fast using very little starting material. It is a very real possibility. While the exact slime yield depends on the specific hagfish species, its size, and how violently the water is stirred, the fundamental mathematical leap from a few milliliters of fluid to massive liters of gel is a structural miracle we want to replicate. By the way, if you enjoy exploring clear, strange nature stories and diving deep into the bizarre mechanics of life, you will love the rest of Faunary. Subscribe to the channel if you want to discover more wonderful creatures that completely bend the rules of biology. Let us return to our jawless wonder one last time. It is truly worth saying again. There is absolutely no venom here. There is no toxic poison. There is only incredibly smart physics. The hagfish carries almost nothing of its own, just the biological seeds of a defense. It recruits the crushing weight of the ocean itself, building an instant, impenetrable fortress out of seawater on a moment's notice. The hagfish has figured out that it does not need to outswim danger. It simply turns its attacker's fundamental need for breath into an immediate hazard. In a harsh, deep-sea world, defined by sheer speed and razor-sharp teeth, this ancient fish wins every time, with nothing more than patience, flexible knots, and a ghostly cloud of living lace. Thanks for exploring with Faunary. If this incredible survivor made you look at the ocean a little differently today, make sure to subscribe and drop a like on the video. There are plenty more extreme adaptations and deep-sea marvels waiting for you on the channel. We will see you in the next one.